Hello students, welcome to the first lecture on magnetism and matter. That is, it is chapter 5 of our NCERT textbook. I am your tutor Mayur Sharma, and in this lecture we are going to discuss about basic concepts of magnetism and matter. That is, you can say that this lecture is based on introduction of magnetism and matter. Not only this, in this lecture we are going to discuss about magnetic field as well as the properties of magnetic field lines, and at the end of this video we are going to compare the quantities related to electrostatics and magnetics. So let us start this video lecture.
Students, you will be surprised to know that the magnetic ore deposits were found as early as 800 BC. That is, we came to know about magnet in 800 BC. Shepherds on the island called Magnesia had a common complaint that their nails of the shoes were getting stuck to the ground. The ore or the stone of that island was given name as magnetite from Magnesia, right? And Greek observers observed that the magnetite, that is Fe3O4, attracts the piece of iron. And the Chinese were the first to use or to make practical use of this magnet for navigation on ships. So actually we started making use of magnet, that is magnetic compass, in 400 BC. So some of the commonly, now Earth itself behaves as a magnet. We know that Earth has its own magnetic field, and hence we can say that Earth behaves as a magnet. Now as shown in figure, it is clear that the magnetic field lines of Earth emerges out of the southern hemisphere, that is from south pole of the Earth, and enters the north pole. Now remember, we know that the magnetic field lines for a bar magnet emerges from north pole and enters the south pole. This is exactly opposite to that. So the reason behind this we will discuss later on, but right now you have to remember that the magnetic field of Earth emerges out of the south pole, that is southern hemisphere, and enters the northern hemisphere, that is north pole. So we can say that the Earth behaves as a magnet with the magnetic field pointing approximately from the geographical south to the north. Now, as shown in figure, let us consider that a bar magnet is suspended from its midpoint such that it can rotate freely in the horizontal plane. Then it continues to rotate, that is oscillates, until it's aligned in the north-south direction. That is, the bar magnet will arrange itself in the north-south direction. Now here, the end of the magnet pointing towards the north of the earth was given as magnetic north pole, while the end which is pointing towards the south of the earth was given as south pole of the magnet. Now here the confusion will get clear. We know that like charges repels each other, whereas unlike charges attracts each other. In the same way, north and north pole of a bar magnet repels each other and north south attracts each other. So the end which is pointing towards the north of the earth, right, must be the south pole of the magnet. But since it is pointing the north pole of the earth, it was given as north pole of the magnet. Clear? And the point which is the end of the magnet which is pointing towards the south pole of the earth must be the north pole of the magnet. But since it is pointing towards the south of the earth, so it was given as south pole of the magnet. The name was given as south pole of the magnet. So here, when a bar magnet is freely suspended, it points in the north-south direction. The tip which point to the geographical north is called the north pole of the magnet, and the tip which points to the geographical south is called the south pole of the magnet. So I think here that confusion will get over, right? So here you can say that the north pole of the magnet is actually the south pole of the magnet. right? So magnetic field comes out of the north pole of a bar magnet, that is actually the south pole of the bar magnet, right? We have given name in a different way so that the end which is pointing towards the north will be known as north pole of the magnet, and it will be easy for us to identify the direction or to find the direction. Now, as I have said that the like poles of the magnet repels each other while the unlike poles of the magnet attracts each other. So here we can say that when a north pole of a bar magnet is brought closer to the north pole of another bar magnet, then they both will repel each other. In the same way, when the south pole of a bar magnet is brought nearer to the south pole of another bar magnet, then also we will see that both these poles will repel each other. On the other hand, if you bring a north pole of a bar magnet closer to the south pole of the bar magnet, then it is found that both these poles attracts each other. So here, as shown in figure, you can say that in figure A, when the north pole of a bar magnet is brought closer to the south pole of the bar magnet, which is hang from a rigid support so that the bar magnet can rotate freely, then it was found that the south pole of the bar magnet which is hanging will get attracted towards the north pole of a bar magnet. On the other hand, as shown in figure 2, when this north pole of a bar magnet is brought closer to the north pole of the hanging bar magnet, suspended bar magnet, then it was found that the suspended bar magnet will move away from the north pole of the bar magnet. Right. So here you can say that there is a repulsive force when north poles or two south poles of the two magnets are brought close together, as well as you can say that there is an attractive force between the north pole of one magnet and the south pole of the other. So in short, you can say that north and south will attract each other while north pole of the two magnets and the south pole of the two magnets will repel each other. For an electric dipole, you may have a separate positive and negative charge. But in case of a magnetic dipole, that is a bar magnet, it is impossible to have a separate north pole and the south pole, right? That is, we cannot have a monopole of a magnet. If you divide a magnet into two parts, let us say as shown in figure, if we cut a bar magnet in two parts, then we will not get a north pole and a south pole separately, right? So if you divide a magnet, then both these pieces of the magnet will act as an individual bar magnets with north and south pole for each magnet. If you further keep on dividing the magnet into numbers of pieces, we will always get magnetic north and magnetic south poles, right? We cannot get an isolated north pole as well as an isolated south pole. That is, monopole of a magnet is not possible. Clear? So here we can say that we cannot isolate the north or the south pole of a magnet. If a bar magnet is broken into two pieces, we get two similar bar magnets with somewhat weaker properties. Obviously, if you divide the magnet into two pieces, their magnetic field will decrease. The magnetic field strength will decrease. Unlike electric charge, isolated magnetic north and south poles known as magnetic monopoles do not exist, right? So we are not having magnetic monopoles. Now, the magnets can be prepared from iron and its alloys, right? So you can prepare magnet, or you can say that it is possible to make magnets out of iron and its alloys. In 1269, a Frenchman named Pierre de Méricourt mapped out the direction of magnetic field lines on the surface of a spherical natural magnet by using magnetic needles. Now what he did is he took a spherical magnet, or you can say that a natural magnet in a form of a sphere, and
He kept magnetic needle at the different positions near that spherical magnet. Now he observed that when he joined all those lines, right, he observed that the direction of magnetic field lines formed on the sphere were passing through two diametrically opposite points, right. That is, you can say that all these lines were passing through 2 points, and these 2 points were diametrically opposite points, which he called as the pole of the magnet. So you can see in this figure, exactly figure I didn't got. So you can see, you can have to consider the vertical lines only. So you can see that all these vertical lines are passing through two diametrically opposite points of the sphere, which he gave name as the pole of the magnet. Now later on many experiments were performed which shows that each and every magnet, independent of the shape and its size, has two poles called the north pole and the south pole of the magnet. So you can say that if you take a magnet in any shape, whether it is a bar magnet or a spherical magnet or a cylindrical magnet, all these magnet will have two poles. One is the north while the another one is south pole. Now we are going to discuss about a simple experiment which you might have performed in standard 8. If you have not performed, then at least you might have come across this concept. Now for this experiment, we will require a bar magnet, a glass sheet or a cardboard and some iron fillings. What you have to do is place the glass sheet or the cardboard over the bar magnet and sprinkle some iron fillings over it. Now you have to keep on tabbing the glass sheet, or you can say the cardboard. Then you will find that all these iron fillings will arrange themselves in a definite manner, or you can say that in the manner as shown in figure. Clearly you can see that they are crowded at 2 points, two opposite points, right, which is given name as north and the south pole. So you can say that as shown in figure, iron fillings sprinkled on a sheet of glass placed over a bar magnet will arrange in such a way that it will indicate that the magnet had two poles similar to the positive and negative charge of an electric dipole. So we can say that magnetic dipole, bar magnet will act like a magnetic dipole. One pole is designated as the north pole and the other as the south pole. Now, when suspended freely, these poles approximately point towards the geographical north and south pole respectively. Now, if instead of this bar magnet, if we take a current carrying solenoid, right, or you can say that DC current is flowing through the solenoid, and if you sprinkle the iron fillings on the cardboard placed above that solenoid, then you will get exactly similar pattern of the iron fillings, and hence we can say that bar magnet and the current carrying solenoid are exactly same, or you can say that they are equivalent. So these were the few basic concepts of magnetic field. And now we are going to discuss about characteristics of magnetic field lines, or you can say that properties of magnetic field lines. You have come across properties of electric field lines, and you will find that some of the properties of magnetic field lines are exactly similar to that of electric field lines. So the first property is, as shown in figure, let us consider figure A and figure B. Here figure A represents the bar magnet and figure B is for the solenoid. You can see that in figure A and figure B, the magnetic field lines are exactly similar to each other. So you can say that for a bar magnet as well as for the solenoid, magnetic field lines are identical. Well, in figure C, an electric dipole is indicated. So you can see that in figure C, electric field lines emerges out from the positive charge and they ends at the negative charge. So electric field line starts from positive charge and ends at the negative charge.
On the other hand, if you carefully observe figure A and figure B, then you will find that magnetic field lines comes out from the north pole of the magnet while they enters the south pole outside, and inside magnetic field lines travels from south to north. So here you can say that the magnetic field lines of a magnet or a solenoid forms continuous closed loops. This is unlike the electric dipole where these field lines starts from the positive charge and ends at the negative charge. So you can say that magnetic field lines always form a closed loop while electric field lines never form a closed loop. Now the second point is the tangent drawn at a given point on magnetic field lines gives the direction of magnetic field at that point. So in figure you can see that at two different points we have drawn two tangents, and these two tangents gives the direction of magnetic field line at those 2 points. So we can say that the tangent to the field lines at a given point represents the direction of the net magnetic field at that point. The larger the number of field lines crossing per unit area, the stronger is the magnitude of the magnetic field B. In figure A, you can see that magnetic field lines at point A, that is 1 and 2. You can see two circles, one at the bottom near the south pole and the second one near the north pole. You can see two small closed loops, right? So here you can see that for loop 1 the number of magnetic field line passing through that loop is very less. On the other hand, for loop 2 the number of magnetic field lines for loop 2 are very large. So you can say that the magnetic field at loop 2 is much stronger than the magnetic field at loop 1. The magnetic field lines do not intersect each other. Remember, you might have come across this concept in chapter 1, that is the electric field lines do not intersect each other, because if two electric field lines or two magnetic field lines intersect each other, then at the point of intersection you can draw two different tangents which will show two different directions at the same point, which is not possible, right? So you can say that magnetic field lines or electric field lines do not intersect each other. For uniform magnetic field lines are parallel to each other and are at equal distance. So if you want to draw uniform magnetic field, then you have to draw magnetic field lines parallel to each other as well as at equal distance. Now at the end of this video, as I have said, we are going to compare the quantities of electrostatics and magnetics. So comparison between the quantities of electrostatics and magnetics. Now in electrostatics we come across electric field, and in magnetics we will come across magnetic field. Electric field is produced by electric charge, while pole strength you can say that is equivalent to electric charge in magnetics. Now the force in electrostatic is given as F equal to QE. So here the force in magnetics will be equal to P into B. Remember, Q is equivalent to P and E electric field is equivalent to B magnetic field, right? So F equal to QE, and here we will get F equal to PB. Now the constant in electrostatics is 1 over 4 pi epsilon naught, or you can say that it is K, small k, right? And the constant in case of magnetics will be equal to mu naught over 4 pi. So if you compare these two constants, you will see that mu naught and epsilon naught are at different position. In case of electrostatics, epsilon naught is in the denominator, while mu naught is in numerator in case of magnetics. So these are the two constants for electrostatics and magnetics. Now the electric dipole moment is given as P is equal to 2AQ, and its direction is from negative charge to positive charge. In the same way, the magnetic dipole moment M is given as 2Lp.
Remember the length of the electric dipole we have taken as 2L, 2A, and here the length of the magnetic dipole will be taken as 2L, and charge and pole strength, right? So P is equal to 2AQ and magnetic dipole moment is indicated by M, and that is equal to 2LP. Or for solenoid you can say that M equal to NIA, where N is number of turns of the solenoid, I is current flowing through the solenoid, and A is cross sectional area of the solenoid, right? So electric dipole moment P is equal to 2AQ and the magnetic dipole moment M is equal to 2LP. Remember this quantity directly we are going to compare. We will not come across the derivation or explanation for this. Okay. Now, the torque acting on an electric dipole kept in a uniform electric field is given as tau equal to P cross E, where P is electric dipole moment and E is electric field. So, on comparing this, for magnetics, we can say that the torque acting on a magnetic dipole kept in a uniform magnetic field is given as tau equal to M cross B. Remember, it is quite simple to derive this equation. You might have derived tau equal to P cross E in chapter 1. Right? In the same way, we can derive tau equal to M cross B. But this is not in our syllabus. So right now we are not going to derive that one. The next is potential energy U equal to minus P dot E. The potential energy of the dipole kept in an uniform electric field, electric dipole kept in a uniform electric field is U equal to minus P dot E, while the potential energy of the magnetic dipole kept in a uniform magnetic field is minus M dot B. Now this equation we are going to derive in our next video lecture. In fact, we are going to start our next lecture from this concept only, that is torque acting on a magnetic dipole kept in a uniform magnetic field, and from that we are going to derive equation for potential energy of a dipole, potential energy of the magnetic dipole. The next is electric field of a dipole. In chapter 1 you have come across electric field along the axis of the dipole as well as electric field along the equator of the dipole, right? Equatorial point of the dipole. So E of axis is equal to 1 over 4 pi epsilon naught 2p by r cube for r much more greater than A. In the same way, electric field along the equatorial point of the dipole is 1 over 4 pi epsilon naught p by r cube for r much more greater than A. So if you compare these two equations, you can say that E of axis is 2 times E of equator in magnitude. Remember, E of equator is equal to minus 1 over 4 pi epsilon naught p by r cube is there, right? But here we have written in magnitude. So by comparison, you can directly write for magnetic field. That is, magnetic field of a dipole is B of x is equal to mu naught over 4 pi. Remember, 1 over 4 pi epsilon 0 is constant for electrostatics, right? So here for magnetics, the constant is mu naught over 4 pi. So in electrostatic, you have 2p by r cube. So in magnetics, we will have 2m by r cube. The length of the electric dipole is 2A, while the length of the magnetic dipole is 2L. So here we will write R is much more greater than L. So therefore the magnetic field along the axis of the bar magnet or a solenoid is mu naught over 4 pi 2m by r cube, where R is much more greater than L. In the same way, the magnetic field along the equatorial point of the magnet will be mu naught over 4 pi m by r cube, where r is much more greater than L. Again, if you compare these two equations, we can say that magnetic field along the axis of a magnet is twice the magnetic field along the equator or the equatorial point. And the last one is electric flux phi is equal to summation of E dot delta S, and by using Gauss theorem you can get this is equal to sigma q over epsilon naught. In case of magnetic flux, phi is equal to summation of sigma b dot delta S, that is summation of b dot delta S. Here remember that magnetic dipole, magnetic monopole is not possible, right? Magnet always magnet is always available in the form of dipole. So for a dipole, magnetic flux is always zero. Remember, electric flux for a dipole is always zero because sigma q over epsilon naught. So for a dipole, one charge is positive while the another one is negative. So you can say that sigma q is zero. So electric flux phi e for a dipole is always zero. But we know that magnet always comes in the form of dipole only. We will not have a monopole, right? We cannot have a monopole of a magnet. Hence, magnetic flux of a bar magnet or any magnet is always zero. Hope you have understand all the concept which we have discussed. You have to write all these concept, right? And of course, if you have any doubt, please let me know so that we can discuss. If you have enjoyed this video, please like and share this video. Thank you.